Okay, hello. Here are a few things I want you to know for fourth quarter. Alright, one, here's our agenda for the next 5 weeks. But we're going to skip that for now. So, our sorting algorithms. Selection sort and insertion sort are two of the ones you are required to know for the AFE exam. These are two that you're supposed to be able to recognize, and then merge sort you will have to be able to explain. And when I say recognize, I mean recognizing code. And they even have to code it. Right now, probably a lot of you are struggling on that. So let's clear some things up. Firstly, that's your method editor with parameter, which you already know, or shouldn't. So there are a few parts to this program. First one is to have this outermost, this big for loop. Notice, there's where that for loop starts, and there's where it ends. That's the outermost for loop. It goes from the beginning until almost the end. It stops at this last one. The reason is because the inner for loop will continue it. It starts at j plus 1. J is the outer for loop's counter variable. If it went all the way to the end, to the 7 over here, and then went into the j plus 1, well, we'll try to exit it, and you'd get an array index out of bounds exception, which would be a problem. So it stops short, lets the inner for loop search through the rest. And what it's going to do is it's going to see if it can find a number smaller than the number it's currently at. So the first time we're going through, we start off with min index at 0. And then if we find a place where the element at this next part is smaller than the element at that part, it'll change the index. So on our first pass, we're noticing that the elements at k, which is 1, is actually smaller than the elements at I, which is, at min index, which is 0. So it's going to change min index to be equal to k, so now it's 1. And it's going to check the next one. So, it looks at k now, k is 2, and the elements at 2 happens to be 2, and that's going to be smaller, and it's going to keep going. Finally, it's going to settle on that one. So that's 0, 1, 2, 3, 4, 5, 6. So min index is going to be 6. So what it's going to do is, it still has elements at j at this first one here. J is still here. Min index is right here. So what it's going to do is it's going to take this other variable, temp, and set it equal to the elements at j. Now j is currently right here, so it's going to equal 8. Then it's going to set the elements at j equal to the elements at min index, meaning this one right here is going to be 1. So it says the elements, and I'm just going to write elem, that is square brackets, at 0 are going to now be equal to 1. So we got rid of this 8, put a 1 in there. Now notice, we had to first save that value, because now we want to put an 8 in here, but we've already removed the data from this slot. So that was what temp was for. So then we go ahead and set elements at min, which is 6, at 6, equal to what temp is, which is 8. Effectively, we have swapped the two values. And that's what selection sort does. It takes each element in the array and swaps it with the smallest element that it can find to the right. So that, and yes, that's true, to the right, because when you go up to j++ again, well, j is now going to be equal to 1, so it's up here now. And then k is going to be j plus 1, so it's going to search through all the rest of these. Now, it might be a little messy and confusing, but let's next step through the rest of this presentation here. So each one is going to search through the rest of the array. And each time we find a smaller element, we do that, yeah. Okay, all that is what we just said. Okay, and this is a basic swap. You will see this a lot. You have some third variable that holds one of the two, the value of one of the two, so that way you can effectively swap them. I might be going a little fast. Put questions on the video or in class, because we're going to do this again in class, if you have any questions. Okay, let's do selection sort now. Selection sort, sorry. Let's do insertion sort now. We finished it, selection. Let's do insertion. So, again, there's method header. Alright, so the outermost for loop will actually this time go all the way to the end. The element it's going to skip is the first one. That's right. Our J now starts here at 5. So that's going to be a little interesting, a little fun. And then our temp variable, we're already using temp, is going to be equal to that number that is that element at J, in this case 5. And then we have this thing called possible index, which I'm just going to write pos for possible index equal to whatever that index is. Currently that's 1. So hopefully you can see how index is 1, elements is 5. Interesting. It's a little different. The reason is this whole algorithm is a lot more like a swap algorithm that also sorts. You'll see. So this while loop, and so maybe see if I can react. Okay, so the while loop is going to search backwards through the array in order to find the right place for our value. So it's going to check from possible index, so long as possible index is not 0, and it's going to keep going until it finds a place where temp is still less than that number. Subtract 1 from it each time. So the first time it goes through, possible index is greater than 0. It is. And temp is actually less than the number at pos index minus 1. Remember, pos is here, as is j. Pos is right here. Pos index minus 1 would be this one. So the elements at pos index, which is 5, temp, which is 5, is less than the number at that index, which is 8. So we say that the element at possible index, which is 1, is going to be equal to the elements at possible index minus 1, meaning this one is now going to be equal to 8. And then we're going to subtract 1 from possible index. So it is now 0. Might rewind if you didn't quite get that. It's a video, I really have no idea if you're getting it or not. That's why I rely on in class so much. Okay, so possible index is subtracted, we get to the end here, we check these again, you notice possible index is no longer greater than 0. So we're done with that. We go outside, and we say elements at possible index, which is 0, equals temp. So now, that's what temp was still for last time, right? We're holding one of the values that we're going to swap. Well, we're still able to do that. Changes this one into a 5. And now you'll notice that this part of the array is actually sorted, meaning our sorting has worked so far. I'm going to do just one more because this is perhaps a little tougher of an algorithm than selection. It's also slightly more efficient, typically. So we go back up to the top. J is now going to be equal to 2 because J++. So J is now here. I might add that in down here. Oh, yeah. So J is now equal to 2, as is elements at 2. That's a little confusing, but oh well. So then we set temp equal to elements at j. So temp is no longer 5, it is now 2. And possible index is going to equal j, which is 2. So we set that equal to 2. And then we're going to go ahead and set elements at possible index, which is 2, equal to the number before it, because temp is less than possible index minus 1. So we change this one equal to an 8. And we subtract possible index by 1. This possible index was up here at 2. But now it's going to move back to 1. And we go up again. Possible index is still greater than 0. And now the number at temp, which is 2, is it less than possible index minus 1, which is 5? Why, yes it is. So we go in. Elements at possible index, which is 1, is going to be set equal to the number before it, which is 5. Okay, and you notice we're getting to that sorted position, 5 and 8. And then it will go through one more time to change this one into a 2, which is what we do at the end. Because now possible index goes down to 0, so we're no longer in there. We go down here to the end, and that's that one last time where we set this equal to 2. 2, 5, 8, yeah. So it's so far in order, and it's going to do it for the rest of it. Okay? Okay, so these are the 5 exceptions that College Board will test you. On which College Board will test you. Okay. We're going to skip these 2 here, because honestly you've seen them a lot, and I think you can understand what they mean just by reading them, or remind yourself what they mean just by reading them. Arithmetic exception you could probably, well, you can see by here, it's anything that would be illegal, null pointer. I'll show you again. And illegal argument I have in a separate video. I felt like the explanation for that one was going to go on a bit long. So here's some code that we can use for some of these exceptions. I've commented them out, and I'll start uncommenting them so that way we can use them. So I'll start with the arithmetic exception. Given some math problem that is illegal, like divide by 0, you'll notice that I'm fine when I compile. The compiler does not stop any of these. No exception is stopped by compiler. But when I try to run it, it's going to give me that arithmetic exception. Basically saying you did something wrong arithmetically. So any kind of operation that would not be okay, like dividing by 0, probably the most obvious ones, will be stopped. And the program will not run past there. So that's the arithmetic exception. I'm going to go through one more. Here it is, the null pointer exception. Given some capitalized data type, some object, that is equal to null, attempting to use it, even though it's null. That will not be stopped by the compiler. While it will stop you if you just fail to initialize it, that will have a problem. But if you do initialize it, or it was initialized somewhere else, in a place far enough away that it didn't catch it, and it's equal to, and it's still null, as in doesn't have a real established existence, it's null, more likely than not it got deleted, and you try to use it, like right here, it's going to break. It's going to say null pointer exception. Because you tried to use something that was null. Remember that null means nothingness, sort of. So this one's actually going to show up in our very next one. Very next slide. We need to have some null checking. Pretty much any object, well, any object really, is going to start at null. If you have not initialized it, yeah, the rules are a little tricky on that. Basically understand it like this. Null is an object that has not been properly initialized, or an object that has been deleted, basically. It's been removed. Primitives don't start at null. They typically start at like 0. But for objects, they also are at null. Objects are things that are like capitalized data types, like string or array list, or mountain, or in this case cat, which is something that I made up, and you guys made up in your labs. It's also things that maybe they're primitives usually, but since they're in an array, they are now objects. So all of these things on the left are null, and all those things to the right are not null. So what is this null checking then? Well, if you try to, as you saw on the other slide, if you try to use an object that has a value of null, your program crashes with a null pointer exception. In the blow code, you'll notice that we make a group of an array of mountains, so those are all objects, but we never actually initialized each of those mountains inside. So then we try to use a for each loop to go through it, and then we try to get the value of one of our elements in that array. Well, it's going to crash right here. It's going to say that there is you are unable to access it because it's a null pointer exception. Okay, but if you make the changes you see here, you're fine. This change right here. As long as you check to make sure that the object you are dealing with is not null first, you will have no issues with your null pointer exceptions. Okay, so remember, check null. So let's talk about integer overflow. Okay, now in real life, an integer is any whole number from, well, I was going to say negative infinity to positive infinity, but those are just concepts, not really numbers precisely. But it's any whole number. However, the data type int, int, is not actually any whole number, just the ones from negative 2,147,483,648 to positive 2,147,483,647. Basically, that is negative 2 to the 31st to positive 2 to the 31st. Now, the reason why it's not literally all numbers, all whole numbers, is because integers are of size 32, meaning that they can only hold numbers that add up 2 to the 0th to 2 to the 31st. Except not really. It's only 2 to the 30th. You see, it only holds up to things which are almost 2 to the 31st or are 2 to the 31st. Can't hold anything above that. Well, negative 2 to the 31st. And that one's actually positive 2 to the 31st minus 1. So this was because the very last binary paste, the 32nd one, which would be 2 to the 31st, is not. It's negative 231st, the smallest negative number. So that means that in the computer, inside it, negative 1 is represented by all ones, because you have this 2 to the negative 31st right here, plus 2 to the 31st minus 1, which equals negative 1. And negative 2 would remove one of those positives. Negative 3 would make it go one more positive. So you see, if a number gets too high or too low, you get overflow, which I'm going to take a quick break and show in this little YouTube video. Once it loads. My connection's... Okay, there we are. So notice, I'm going from just 150 under that largest thing that we said we could have. And we'll see what happens. So notice, it stops right at negative. We'll watch that again. It's going as long as it's positive, and somehow it goes from a large number that is positive to a negative number. It goes from this number to that one. And that's because once you get to this point, once you get to the point where you're at all of them except for the first one as ones, or all of them except for the leftmost one, it increments that one, and the rest becomes 0, and your number becomes negative 2 to the 31st. We call this overflow. So when a number gets too high or too low, you have overflow issues. Okay, and that is where we would leave off. So I hope that's helpful. It's just something to refresh on, perhaps. See you next time.